Let's derive a relationship between the initial and final volumes and pressures of an ideal gas during an adiabatic expansion. We will make the following assumptions. The ideal gas has equation of state PV equals nRT. The relationship between the initial and final volume and temperature, which was derived in the previous video, is T sub I over T sub F equals V sub F over V sub I to the nR over C sub V plus 1. We also assume that nR equals C sub P minus C sub V, which was derived earlier. And we also assume that, we define gamma to be the ratio of specific heat at constant pressure to specific heat at constant volume. And by the way, R is the universal gas constant, little n is the number of moles of gas, T is the temperature, V is the volume. So start by writing the equation of state of an ideal gas. Before and after the expansion. Remember, this is an adiabatic expansion. So before the expansion, we use the subscript I for initial, and after the expansion, we use the subscript F for final. And the equation states PV equals nRT. Then take the initial equation and divide it by the final equation. Cancel the nR since the number of moles of gas doesn't change during an adiabatic expansion, nor does the gas constant. Divide by V sub F over V sub I. Now, use the fact that we previously derived that T sub I over T sub F is V sub F over V sub I to the nR over C sub V times V sub F over V sub I. Now use the fact that nR equals C sub P minus C sub V. Distribute the 1 over C sub V in the exponent. So C sub V over C sub V is 1. And of course, V sub F over V sub I is the same thing as V sub F over V sub I to the 1 power. So you can combine the two factors of V sub F over V sub I by adding the exponents. Minus 1 plus 1 is 0. And if you define gamma to be the specific heat at constant pressure over the specific heat at constant volume, this is the relationship between the pressure and volume before and after an adiabatic expansion. So the initial pressure divided by the final pressure equals the final volume divided by the initial volume to the gamma power.